So hello everyone, welcome to ethics seminar series. I'm John, the seminar coordinator, and I will be moderating this seminar with our communication specialist, Kathy Manley. And just so you know that the seminar is being recorded, and we will publish the recording on our YouTube channel soon. This seminar will have the presentation, which is about 45 minutes. And then we have the Q&A. Please feel free to bring up any questions. You can unmute yourself, or you can chat us your questions. And before the speaker gets started, we'll have our acting director, Ralph Ferrero, to introduce the speaker. So Ralph, please go ahead.
Yeah, thanks, John. Yeah, and welcome Annarita Mariotti from NOAA's Climate Program Office, where she's worked for the past several years. And she directs a lot of their programs and also has served, she spent some time at the White House doing some policy work. And prior to a lot of this activity, she's also done a lot of climate research work, and she's also a visiting scientist at ESSEC as well. So we look forward to hearing her talk about climate projections and predictions and how we're going to get there with some newer ways of thinking about it. So welcome, and we look forward to your talk.
Thank you very much, Ralph. So I guess I'm going to share my screen. All right, going full mode. Are you seeing full mode?
Yes, we see it.
Full screen. Okay, yeah. So hi, everyone. I am very excited to be here, albeit virtually. I know there are a number of sort of old friends on the line, as well as maybe new friends on the line. So I'm very excited to be doing here to give this talk. And this is, so it's about envisioning next generation's US climate predictions and projections. So it's a sort of big picture talk. There are no equations, good news for students. And it's really trying to, if you have an appetite for thinking big picture, this is the talk for you. And the views that I'm going to express, they're my own views, my own perspective, not those of NOAA. I have a number of colleagues who contributed to this, same applies to them. And I will just say that I've come to this topic, as Ralph was saying, first through my research. I'm not a model developer, rather a user of model predictions, projections for looking at climate variability, predictability. And then as I joined NOAA, started to manage a research program. I directed the MAP program, the Modeling, Analysis, Predictions, and Projections programs at the Climate Program Office. And also I co-chaired and still co-chair for the U.S. Global Change Research Program, the Interagency Group for Integrated Modeling, or IGEM, that coordinates sort of modeling for the federally funded sort of programs and activities. And then lastly, from research to management, I landed onto policy, science policy, as Ralph was saying. I spent about 2.5 years at the Office of Science and Technology Policy of the White House, where one of the topics, the policy topics I explored and touched on was indeed climate modeling and climate predictions and projections. So this big picture talk really stems from some of the things I started to think about when I was there. All right, so that's the sort of the preamble, and I like to start with what I'd like you to take away out of this talk. So if you turn off your computer, go asleep, whatever, these are the 3 things I want you to go away, from this talk. Number 1, accelerated progress on next-gen climate predictions and projections is necessary, and it's also highly valuable for all sorts of reasons that I'm going to explain. Number 2, we do have the basis to to do this, to accelerate progress. And then number 3, we have a vision for how this progress could be achieved, this accelerated progress could be achieved. There are other ideas out there, and love to discuss and really move forward. So these are my 3 takeaways, and I've organized the talk across, considering these 3 points. So the need. So first of all, I just wanted to, especially for the students here on the line, just thinking a little bit about, stepping back and what our models are used for, why they're so important. And so I have a diagram here on the left where it shows sort of the different kinds of model of processes that are embedded in Earth system model, or some version of this in a climate model. And climate system models are developed with the use of observations, process research, and so they encapsulate their best assessment of what the processes are like, and allow us to really explore the interplay of these various processes and how they result into, in the kind of variability that we have observed, and also allow us to predict or project what's coming for us. So future change, whether it's an ENSO or future climate change, or long-term, in terms of predictions. So they're extremely, extremely valuable as, again, projection tools, as well as exploring understanding and knowledge. So I would say that, the kind of assessments that are sort of fundamental for climate policy, the IPCC reports, those from the Intergovernmental Panel for Climate Change, really leverage climate modeling very heavily, again, for understanding, but as well as for projection. So understanding sort of the physical basis of climate, the impacts of climate on our activities, on extremes, on trends, etc., as well as exploring sort of climate mitigation policies or responses. Also nationally, climate projections are used as the basis of our national assessments. So we're here in this slide, I have sort of the 4th and 5th national climate assessment. So these are really the basis for stating, the science that's done based on those projections, what we understand regarding the changes that we are seeing, and also what's coming our way. Also, this models, the prediction systems, from the weather to climate timescales are really invaluable, and even economically, socioeconomically, and provide information on projections that is freely available to all, and support a broad array of environmental services, whether it's services for preparedness, to the next extreme, whether it's for agriculture, whether it's for energy, water resources, you name it. There is a model, whether it's an Earth system model, climate model, modeling under that to provide those kinds of predictions and projections. So really valuable. And while our models have been so valuable and are so valuable to help inform climate policy and inform action, inform preparedness, there are new predictive challenges that our community is facing right now, today. We have, every day we see, if you open the newspaper, nobody does that anymore, but your whatever favorite news stream, you can read about extremes, whether they are fires, whether they are droughts, inundations, very extreme storms, extreme heat in the summer. So these kinds of extremes are becoming more frequent. They're becoming more severe. And people just need better information, not only on the physical risk, but also how the physical risk, gets to the hazard that they care about, whether it's, inundation for their property or their, business, how their supply chain is going to be affected, etc. So there's this increasing interplay between the need, the sort of physical risk and information that people want for what they care about. And we increasingly are sort of challenged to get all the way to that. So it's information for preparedness, for resilience to these various extremes. People also, especially policymakers, really want to know what's coming our way that potentially could be just a sort of game changer, like an irreversible change in the way that we that we live. So those sort of what we call tipping points. And so, is there a chance for a dieback of the rainforest, or a meltdown of the ice caps, or shifts in the in the distribution of species? We already are observing, of course, this kind of changes, but kind of things that are really big and irreversible. And of course, they're very interested in all the questions that pertain to security. So, what is that going to do to different, people, and can that result in migrations, etc. So there are, again, new predictive challenges for preparedness and resilience. And I put here in this slide just to kind of nail this down. The front cover of a recent report by the President's Council of Advisor on Science and Technology that came out last spring. And this is a body, the PCAS, that looks at all sorts of science and technology things, not just weather and climate, but they actually had a report specifically on extreme weather risk in a changing climate, just to say how important this is in their mind, and the need to enhance predictions and protecting communities. And quote, $1 trillion of damages from extreme weather, with in 1 year alone, over 3 million Americans displaced for their homes because of the extreme. So they recommend really focus on climate science and computing to provide significantly better information about the physical risk, really empowering household communities, etc. So again, so consequential, the kinds of information that we get out of predictions and projections for practical purposes. And so also, adding on, the predictive challenges are also because we are increasingly using predictions and projections, sort of analysis based on these models, to inform solutions for climate adaptation and mitigation. There are some of these very, very expensive, and there are things that are infrastructure that are going to stay around for 30, 50, 100 years. So really, we want to have the best information at the fingertips of the decision makers, the policy makers, as they make those decisions. And here, just as an example, I have, people deciding, what kind of, crops should be planted, and whether the way that farming is done in a way that maybe can capture more carbon, again, thinking about climate mitigation, or resilience at the coast, and how that can also help to capture carbon, or different, adaptation in our infrastructure, transportation, or cities, again, for climate adaptation. Here I have examples of infrastructure for renewable energy, as well as carbon capture, direct carbon capture. These are things that are very expensive, and we want to have the best information available to make those decisions of where to place them, how to build them, etc. And there is climate finance economy is really very tightly coupled here with all of this information. So again, very consequential, so from a monetary point of view, to have the best information available. So in what ways could sort of predictions and projections be better? What is this next generation that would sort of support an expanded set of services? So here I have a few examples of things that I think would be really valuable. So number one, we have persistent model errors, biases in our models, and those do influence the capabilities of models to predict and project. So having models with reduced errors would be very valuable. Representation of extremes, some of the photos, the images I showed you there about extremes, so whether it's tornadoes or a hurricane or fires, some of these the processes or even the extremes themselves are not well represented in our models. In part is resolution dependent, in part is processes. So having a better representation of extremes would be very valuable. And then getting to the human systems. So I told you about how, people are increasingly interested in this interplay between the physical or biogeochemical and the human systems, having more sort of the enhanced capability of having this interplay within our models in some form would be very valuable. And also, I told you about like cascading hazards. So people are really interested in, okay, so there's going to be a hurricane coming my way, but what is that going to do to my power plant? Will there be, let's say, an oil spill in this area? How is that going to impact fisheries? So it's really the ensemble of cascading hazards that is very valuable to people, to cities, to governments, etc. So we want to have, if possible, those types of modeling capabilities. Uncertainties. People want to know, the best estimate of uncertainty. What is the worst case scenario that can happen? They want to know that. So really explore uncertainties. The full range of uncertainties is something that's paramount. Customization. So, people have specific questions, whether they're a city or they're a business or maybe a large business. They want answers to specific questions they may have, right? At this point, people have to kind of deduce that from some projections or predictions that are out there somewhere, and then there's can be tailored. But some questions really depend on targeted analysis simulation. So increasing customization and translation of this information, rapid translation of this information into, what happened, how do we go from the science, from the modeling to what I need to know? That would be very valuable. And then also, last point I will bring up, so we have models to look at climate change, climate interactions, and then this typically that's working group 1 of IPCC. Then we often have another set of models that looks at the impacts, downscaling those global climate models to a level of a state or a city or whatever. So. And then we have also another set of models, so integrated assessment models, sectorial models, to look at responses, so very sort of simple representations or simplified representations of human activities to start to study this response option. So it's a cascade of models, and potentially there could be better connection or consistency across these various sort of working group 1, 2, and 3 set of models that are used for climate assessments. So in summary here, I'm summarizing, it would be great to have projections that have higher horizontal resolution, maybe finer than 10 kilometers, that represent extremes, the ones that we care about, and associated risks in greater detail, with reduced model errors and better estimates of predictability, so the uncertainties, and just more customized so that they can support the next generations of climate services that people are thinking about. So that's the motivation. So the basis, it's wishful thinking to say we need X, Y, and Z, but is this feasible? What's the basis for doing this? So I'm going to articulate a few reasons why we think that this is feasible. First of all, we have a very strong US enterprise as basis for this progress. We have federally funded climate modeling groups and programs. These are funded through the US Global Change Research Program, with a number of agencies behind these that have sustained, these efforts over decades, and again have resulted in the kind of information that we have now. And then we have programs, that involve the broader community. And here I have some examples, Cliver, GeoX, etc. But there are others, very strong U.S. academic research sort of enterprise that is very much engaged with the sort of federally funded climate modeling groups and programs. There's also a number of private sector players that are relevant and potentially very useful here. So I'm talking about philanthropies as well as commercial entities. And then, of course, we will work with all our partners internationally, collaborate on all sorts of projects under the WMO, the World Meteorological Research Organizations, as well as the World Climate Research Program, WCRP. So we have the basis in terms of like the know-how people here in the US in this enterprise. Just a little bit more on the federally funded climate modeling group, especially maybe for the students. I thought this would be helpful. So there are pretty much 6 centers in the US that are federally funded, that provide information for predictions, projections for the CMIP or operational predictions. So the Community Earth System Model by NCAR, the CSM, then that focuses primarily on science, involving the community, engagement of the community, through this sort of a CSM project. The E3SM, or Energy Exascale Earth System Model, funded by DOE. The primary focus is really supporting any energy applications, of course, as well as the use of new technologies to do this. 2 models by NASA, sort of the Goddard Institute for Space Studies, GISS, and the Goddard Earth Observing System, or from GMO, the GEOS model. So the NASA models, they of course, focus on the use of NASA observations in general, as well as supporting NASA missions and understanding sort of the Earth system data simulation, those kinds of things. GISS in particular focuses on the role of aerosol and forcings, and how they sort of play into determine the climate that we have had or we have now. And then GEOS is more on the sort of the forecasting of weather and seasonal conditions, as well as the current climate or conditions, again in support of the NASA sort of missions. And then from NOAA, GFDL, the Geophysical Fluid Dynamics Library, GFDL, and the Unified Forecast System. So NOAA is very focused on saving life and property, practical information, predictions, and projections to support the economy, and the whole sort of suite of modeling, predictions, and projections that's needed to do that. And coordination across the centers is facilitated by the U.S. Global Change Research Program. And so while the centers have each, they're driven by the mission of their agencies, they have a number of really areas where they share priorities as well, so they share challenges. So this diagram here is sort of summarizes the current U.S. climate modeling landscape. So you see the federal agency priorities driving what the modeling centers do, the federally funded modeling centers do. They all use sort of observations for understanding data simulation, data analytics, etc. They all collaborate closely with academia, as well as private sector and internationally. And then they sort of deliver a number of products, whether they're projections, predictions on seasonal decadal timescales, reanalysis. And then the sort of users or service providers have to kind of go to some portal somewhere, download the data, try to, do whatever is needed to get to the answers, the service they want to provide. Largely, is like that. Although some of the modeling centers, for example, the NOAA centers have that sort of service delivery mission. So, things are more integrated than this. All right. So the basis for next generation U.S. climate predictions and projections. So I told you about what I think are the pillars of the U.S. enterprise. I also told you, the directions where we think we want to go. And there are scientific and technological opportunities that really provide, I think, the basis for accelerated progress. And, to be very clear, all our modeling centers are already doing and working in these various directions. So it's just a question of, can we accelerate progress? Can we be more responsive? So in terms of scientific opportunities, all our modeling centers are working on very high spatial resolution for improved realism. That's something I'll talk about more in a sec. As well as very large ensembles to harness, understand predictability, to quantify uncertainties, as well as sort of advanced data simulation methodologies like coupled data simulation, to really, again, get the most use out of the observations, if you will, to initialize predictions and forecasts. And thirdly, our modeling centers, some of them are really thinking and working very actively in this sort of global to local weather to climate modeling systems, so systems that can be applied across timescales from weather to climate, which of course enhances the confidence and sort of robustness of the projections, as well as systems that can be utilized, for both studies of what global change, as well as zooming in on a particular area to get to the local information that people need. So this is a set of scientific opportunities. On the other side, technological opportunities, we now have, as a reality, exascale computing and data storage available. It's not dedicated to our enterprise, to climate modeling, but it exists. It's a reality. We also have this sort of explosion of sort of data analytics, machine learning, artificial intelligence, that's really getting so much more information out of observations, out of models, as well as allowing us to sort of fuse together, if you will, modeling data. I will talk about this in a second. And can be really impactful for all sorts of applications, to accelerate our simulations, to improve some of the biases that we have, have larger ensembles, all sorts of applications. And then thirdly, but not least, we do have infrastructure for co-production, things like this, the virtual meeting that we're having now, or platforms, cloud platforms, all sorts of types of infrastructure that can support more co-production or enhanced co-production of information, so that the information is more actionable, and the sort of pathway between the science and the service and vice versa is quicker, is expedited. So I'm going to give you here sort of a number of touching on the points I just talked about, but a little bit more on some of the points based on previous work, previous publication by other groups, again, as the basis of what we are thinking about. So in 2012, there was a very influential report by the National Research Council titled Advancing Climate Modeling. And this particular report, had a number of very good recommendations. One of the things that they recommended was really to try to have more of a common software system across the modeling centers. In general, have components that are that can be more interoperable, so that can be interchanged across models. And so that was one of the things that they recommended, really to bring together some of the capabilities that we had that maybe at this point are not as widely sort of useful or shared. So that's one thing. They also, they were also thinking about this, modeling community, service community, so this interface. And so one of the things they recommended was an annual US Climate Modeling Forum to bring together both the modeling and the users of climate data. They also included a number of recommendations vis-a-vis the science, kinds of things, the kinds of things I just talked about that could really advance climate modeling, increases in resolution, new types of observations, improvement in the physics of the models, to have really more complete representations of the Earth system. And then also recommendations vis-a-vis computing, have sort of climate dedicated computing resources at the modeling centers, and also ways to exploit the kinds of new systems that were coming their way. It was 10, 20 years ago, right? 10 years ago now a reality. So another, so talking about high resolution. So one very sort of promising direction is to have models that go to very high resolution kilometer scale at the global scale. And the rationale for doing this is that if you are able to get to kilometer scale, you can simulate some of these sort of fine-grained features, whether they are, tornadoes or cyclones in the atmosphere, convection that underpins some of these, this phenomena, as well as oceanic eddies patterns. You can better represent orography. Currently, if you have, 100-kilometer or 50-kilometer model, this is smoothed. So definitely sort of benefits for these things, and with the idea that this would result in a greater realism of the Earth system. And the rationale there is just sort of thinking of the sort of propagational error, upscale propagational errors, from the local scales to the larger scales. So it could potentially also impact larger scale phenomena like, I don't know, the NGO or ENSO, things like that. And also, the idea that if you get to, let's say, the scale of the cloud, you can start to reduce the need for parameterization, which is what we use for anything that we can resolve directly. So anyway, this is really an area where our modeling centers, as well as the broader community, academia, has been very active. Here, I have a diagram of like a photo of a sort of convective scale global modeling set of experiments. This is the diamond intercomparison of global cloud resolving models. These, in this case, these were like atmosphere only models forced by SSTs, but really they were looking at specifically sort of what does the atmosphere look like when you go to very high resolutions. And then also, I was talking before about the sort of global to local scales. There's this emergence, and now several modeling centers have this capability to have global variable resolution models, where you can have very high resolution in a particular area that you want to apply it for whatever reason, and you can do from your climate projections potentially, if you have the compute, all the way to the tornado outbreak for your weather forecast. And we have at NOAA examples of doing this, and this is a slide courtesy of our colleague at GFDL, Lucas Harris. Also, I talked about the emergence of massive data, new data that's now available, that's providing new sort of opportunities, including from the private sector. Commercial sector is launching small satellites. Different types of observations are coming online that we can exploit, for the kinds of things that we care about. I already talked about the high resolution modeling, to resolve key processes, as well as the emergence of machine learning. These three things are kind of converging to create new opportunities. And this is a slide from a colleague, Pierre Gentine. So converging to stimulate the creation of what people call sometimes digital replicas of the Earth, or digital Earths, digital twins. There's different terminologies. There was a recent actually study by the academies on digital twins. So a very nice study. I encourage you to go take a look at that. In this case, again, the convergence of observations, high resolution modeling, and machine learning, artificial intelligence is being applied to try to have very high sort of resolutions, very high resolution visualizations of the Earth. In this case, on the left is this is the project by people at Max Planck, the Earth visualization engines. There's a sort of a movement in Europe to do something like this for the purpose of allowing people to better visualize the climate change that's happening around them, understand options, etc. And then Destination Earth is another very high-level example in Europe, very prominent example, where ISNDRF is getting involved with other partners in the community for the development of this sort of digital twin. Basically, the in a nutshell, what they want to do is to run a very high resolution model, and then in parallel with observations, kind of through machine learning, artificial intelligence, get the observations inside the model to have a replica, so a computer model of the Earth, and for applications from weather to climate adaptation. So that's in process. On the other end of the spectrum, I would say, there is sort of view. Here is a report from the World Climate Research Program from March of 2022, where they're really emphasizing the need for more of a multiverse of climate modeling systems. So rather than have one sort of modeling system that you run at a very, very high resolution, and to get, as I just talked to you about, in the last two slides, the idea here is to have more of a multiverse of climate modeling systems to do different types of experimentation, including the very high resolution one, but also have the flexibility to do different types of science, because that's what they argue in this particular report that's needed. So what are we thinking about? So now I'm going to come to our vision, and this vision is described in a paper that we submitted to the AGU Earth's Future. It's currently in review, and the co-authors of this paper, I will just also say that these are sort of the leaders of the federally funded climate modeling groups in the US, across the 6 centers I just talked to you about, sort of from weather to climate. And so I think this is kind of unprecedented. For the first time, we have like something in writing where we provide our own personal perspective. We're not representing our agencies here, but we are giving our personal perspective on ways in which we think we could as a community accelerate progress. And we give this out for the purpose of discussion. So we fully expect that there will be other ideas out there, and hopefully there can be sort of momentum towards this next generations of predictions and projections. So, but anyway, if you want to find out more, go to the paper. Otherwise, here I'm going to give you in a nutshell, in a few sort of conceptual diagrams, what we have in mind. And the rationale for this vision, which builds on the ideas I just talked to you about, all these ideas I talked about are really useful and sort of informing what we had in mind. It has this rationale has 3 legs. So number one, we really want to be grounded in climate science, and at this point we fully understand that there is no perfect model. We still have uncertainties on representation of processes, and so picking one model and going to very, very high resolution with that model, and that would not deal well with uncertainty. So we need to have sort of multiverse or an ecosystem of models to gauge uncertainties. And also, there's so many applications of that, as I told you about in the beginning, that it's really important to have sort of this flexibility to set up, the experiment, the prediction simulation in a way that addresses, a diverse set of applications for the various agencies that are being supported. So the second leg of the stool is we want to build on the strengths of the community, of what we have right now that's been funded for, many years, whether it's within the centers or in the community. We want to build on that and expand from there. And the focus is really, we know that there are shared priorities, right? Shared priorities across these modeling centers. People are working on, in many cases, on the same things, whether it's high resolution or, other things, machine learning, computing, all of that. There's common opportunities as well as common challenges across the modeling center. So what we are trying to do here is to say, let's focus on the collective action, on these shared priorities, this sort of enterprise scale opportunities and challenges, big things that nobody can really do alone, and try to augment what agencies have already planned to do, augment that so that we can get to bigger things with an unprecedented level of US coordination. And there are 6 pillars to this proposed vision. So I will walk through each one of them in the next few slides. So first, transformative science. So based on what, again, I've told you about the various things that are going on, where the science is, we think that, these 4 areas, so focusing on very high horizontal and vertical spatial resolution, and also reducing model biases is something that's shared priorities across the centers that is promising, that could be really transformative. Another one related to this is this thrust to go from global to local in our system modeling to improve the way that we represent processes that works across scales, that supports the kind of very high resolution I just told you about. And also go to sort of really ways in which we can harness the predictability that's in the system. So understand, what kind of observations are available, how to best utilize them. So advanced ways of doing data simulation, as well as large ensembles to really help quantify uncertainties and all the kinds of course, methodologies that are associated to these things. And then the last area, enhanced integration of human systems in the sort of physical biogeochemical Earth system. And by enhanced integration, I just want to make it clear, we're not advocating for full coupling of everything into everything. I think it's really a research question, what's the kind of integration that makes sense for application X or Y. So it's really like the research and the capability to understand what makes sense in a way that we can get to the answers that I talked about in the beginning, so that the information that gets all the way to the human systems, but in ways that make sense. Because every time you add a process in a model, you add uncertainties, you add complexity. So you really want to do this in a way that's very thoughtful. All right, so the way that we want to tackle this is really through collaboration and having a set of collaborative and evolving goals, complementing and augmenting what the modeling centers are planning to do. They each have, of course, their modeling plans. So these are areas where we think that there can be convergence and potentially really acceleration of progress through this convergence. And then, having an approach where we really judge the success of the enterprise, by looking at what are we able to do nationally. For example, for the national climate assessment, what's available nationally in terms of predictions and projections. So having that sort of enterprise scale way of judging success. Common science thrust, I already talked about this. And then, having sort of interdisciplinary teams of experts across the centers and the broader community. Here I'm talking about academia, I'm talking about internationally, having on this sort of foci area of thrust, having teams of people that can work together. We have some very nice examples of success here. For instance, we have, for example, climate process teams have been judged very successfully in the way that they improve process modeling. So that's one particular application, but one could envision, teams that are for other, other areas, these other areas that I mentioned that are, again, interdisciplinary and highly impactful. So that's pillar one. Pillar two has to do with really getting the juice out of the modeling that we do. So really expediting the science of service pathway and having co-production information so that the information, the predictions and projections that are produced are most useful and used, right? So and this really stems, I think the basis here is to have the modeling community and the services community really more better connected in a seamless way. And so envisioning sort of teams that are, with experts that are across these various, modeling and services community, experts that can sort of straddle the two, common frameworks and metrics. for instance, there was a recent workshop looking at projections, downscale projections. Having framework that both the sort of the modeling community and the service community, that's common, where we can judge value and metrics to do that, be very valuable. New types of products that are again help to tell that story and address questions that the service sort of enterprise has. Again, co-production of these products. And then I wanted to emphasize sort of equitable access here. I think it's really important that the best available information from the modeling, projections continue to be available to all. And so having sort of the federally funded work, really be available to this broad service enterprise and to anyone in the public is really crucial, and something we want to make sure stays very visible here. And supporting this sort of interface, a simulated interface and co-production between modeling and services through a data storage and analytic platform, which I will talk about in a minute. So I think so the idea here is co-production, so we can really be delivering things that are more customized, that address public needs, that are more timely, so not necessarily on a 7-year sort of cycle like the assessment reports, but maybe more rapid, depending on big questions that arise, whether they are policy questions or things of national scale that need to be addressed that one can organize around. All right, so getting close to time here, I see. So high-end computing modeling. So we are envisioning sort of a federated computing infrastructure. So this is potentially distributed, but dedicated to this problem, to sort of climate modeling, potentially a hybrid of CPU, GPU, for joint experimentation on these priorities I talked about, like priority 1 and 2, right? So an ecosystem of high-end agency models, data and workflows that can support the kind of transformative science I talked about under Pillar 1, but also the staff, to the software engineers to have performant code, portable code, to really be able to analyze, execute these very complicated large experiments, large ensemble experiments, or very high resolution experiments. And then here on the right, there's an interface, again, just like for the services, with the data storage analytics platform. That's a Pillar 4 for execution analysis and visualization. Pillar 4 is this data storage analytics and observation focus or pillar. And this is, again, on one hand, there is the modeling that needs to be supported. On the other is the services. In the middle is really this capability to store data in a way that's efficient. Right now, we have pretty much every modeling center has its own data repository. So, if to put out the data, they all have to a large extent ways to do that. But here is thinking about ways to do this that's more efficient. So we're thinking of exascale data storage, a flexible hybrid of physical and cloud storage potentially to support for access to observational data, model data, for R&D, but also utilization across the modeling enterprise, and also for data analytics to support sort of the co-production of actionable knowledge, as I just told you at the beginning, to go from data to actual useful information. And then at the bottom in the slide, the kinds of data analytics that you need to, and workflows and metrics that you need to really process, whether it's observational data or model simulations for all sorts of purposes, the incorporation of new, improved, diverse observations, having predictions, projections, hindcast and reanalysis there, and then again, the workflows and analytics to support the services. Number 5 is the sort of skilled, diverse, interdisciplinary workforce. That's so important. We need sort of the skilled experts that are across the various disciplines that support this type of work. So you see here examples of so the areas, whether it's modeling, whether it's co-production of action information, whether it's sort of the infrastructure, and really, thinking about how we can enhance and diversify pathways from academia to the modeling centers, provide access to students, professionals to continue to develop their career goals and get into the enterprise, and really ensure that we have sort of long-term career track employment and retraining and training opportunities, as well as sort of an eye to potentially new promotion and reward system to keep people in the enterprise. So last but not least, very important to continue to augment the current partnerships and collaborations that we have, whether they're domestic collaboration as well as our international partners, but thinking also together, in a more coordinated and strategic way to new types of collaborations with potentially philanthropies, the commercial entities, as well as some of the players I mentioned before, in a way that's bilateral. If we have common goals, there could be collaborations internationally on some common thrusts. This slide here is just to, sort of in a nutshell, is a summary of what I just told you about, how we go from where we are now. I showed you at the beginning, towards the beginning, the current landscape. This would be an evolution of the landscape where there's this sort of the modeling centers working on this shared cross-agency shared priorities. That's the focus here. And then the 4 pillars, so transformative science, computing, co-production, and data. And then left and right, the other 2 pillars, workforce and partnerships. And I think what's really important here, the difference is thinking of this, at the outset, about this seamless sort of interface with the users, with the service providers, and platforms and teams to do that, to do this, to support this. So I think I'm running out of time, so to leave a little bit time for questions, I'm going to skip this. There are tangible outcomes out of all of this, and they speak directly to the needs that I mentioned at the top. And so there's very good reasons to think about accelerating progress. So these are my takeaways. Hopefully, I have convinced you that it is sort of necessary and highly valuable to accelerate progress here on predictions and projections. And we have the basis to do this. And there is a vision that people have ideas on how to do this, and we should discuss and make progress here. So thank you for your time and attention.
Thanks, Annarita. We have a couple minutes for Q&A. So there's one in the chat from Nancy. So Nancy, you can go ahead and ask your question. Oh, but I can't hear you. You're also noted.
Hello.
Hi.
I was looking at slide 16. I think I look at slide 15. I was thinking about the grid, the shape of the grid, but somebody else in the chat answered that question for me. Lots of people done this work, but is this something you're thinking about too? Like considering different types of resolution shapes besides squares?
Yeah, I mean, people are experimenting with all sorts of types of variable resolution, methodologies. There's zooming. There's different types of ways to get from global to variable resolution. I've not seen the chat. Hopefully, people are agreeing with me. So yeah.
Oh,
absolutely.
And one more is, have you considered the dangers of machine learning in terms of the computer could control everything and the computer may spit out wrong results and retrain it already, and how are we going to change it back?
Nancy, you're spot on, and I think there's a lot of sort of thought that's going to how machine learning is being applied to this field. I think we want to do it in a way that's very responsible. So absolutely, the things you raise are concerns, and so I think again there are ways that can ML AI can be applied. It's kind of no-brainer, emulators
okay.
Yeah,
You still
but there are
gotta
also things that are tricky.
Every little piece you have to have a check to make sure the computer doesn't spit out wrong results. That's kind of hard, though.
Yes, so that's that's why we need what people talk about explainable AI, or really make sure that we have the scientists that continue to be able to assess whether what's coming out is making sense, from a physical point of view. But also there are, methodologies that are hybrids of ML/AI and physical base. So there's ways people are really attacking this. But you have very good points. Thank you, Nancy.
Thank you very much. I'm done.
Thank you. Dr. Lee also wanted to ask a question. Dr. Lee, go ahead.
Hi, Anna. Thank you very much for the very comprehensive review of programs on climate change and modeling. So my question is concerned with your talk about U.S. global models, climate system models. We have 6 models. Married, but it's not so clear how these models or the model people have interact, and how do they really come up with something that can be beneficial to other models. One thing we talk about for a long time that U.S. has many models, but as far as weather forecast and the climate, it may not be the best in the world. European standard model often considered as somewhat better. So is there really very much effort being made to unify the model and to make it the single one or the the overall best one around the world, in the world?
So thank you, Zanchin. Good point. So remember the rationale I explained as 3 legs, right? So one leg is we think that for the climate problem, there is no single model that you can take and say, I'm going to take this and I'm going to be bulletproof. I know what the future is. So there's significant still uncertainty in process models that underpin the various models. So diversity is actually gold. So that's why, again, the weather problem is, in a sense, a little bit different there. There are different type of processes at play, the coupling, but that across the various interfaces of the Earth system that result in weather and weather forecasts are a little bit different from longer timescales. And a lot of the processes still are uncertain, and so having that diversity of modeling is really important. That's why we have a couple model intercomparison project in the US. We have an annual US Climate Modeling Summit where we actually confront results. What happens if you go to high resolution? You will have diverse answers because the different models, climate models, have different process models underpinning those. But that's an important point you touched on. Thank you.
Thank you.
Thank you. So it's 3 o'clock. So we have to let our speaker go. But thank you so much, everybody, for coming today. And thank you, Annarita, for coming to give us this great talk. I just want to remind everyone, so next week is UMD spring break, so we don't have a seminar on Monday, but we do have a working group meeting on Thursday that you should all have emails from me in your inbox. So please come to that. Let me know if you have any questions, and have a lovely week.
Just want to say thank you before I go. Thank you for hosting. This was fun.
Yeah, thank you. Thank you for giving this great talk. Another thing I wanted to say is that if you wanted to, you could come back in the fall if you wanted to schedule in person talk.
Sounds good. We can talk about that. Sounds good.
Cool. Okay, and I did send you.
I'm sorry if I went too long. So yeah.
Oh no, it's fine. It's all. And I sent you the invite for Thursday, by the way, just in case you're interested.
Sounds good. Thank you very much.
Cool. Yeah, of course. Have a good afternoon.
Thank you, John. Bye-bye.